Use substitution and definite integrals. Okay, so once you could do this, again, which is used to find area or volume of something, then it's just applications, okay? So let's see how this works. All right, so I'm going to let u equal x squared plus 1. So du would have to be 2x dx. Okay, well I have an x dx. I'm going to put a 2 here and a 1/2 outside to balance it, because half of 2 is 1, and multiplying by 1 does not change a value. So I'm going to have 1/2 integral, and just for memory, this is du, and this is du, and this on the inside is u. So I get u cubed du. Now what I need to do though is also change my limits of integration, okay? So I'm going to put a big note on here. Change limits of integration. Okay, I'm going to underline that twice because it's really important. Okay, so if I substitute 0 in for x, I get 0 squared plus 1 is 1. If I plug in 1, I get 1 squared plus 1 is 2. So now I've changed my limits of integration. So now I have 1/2 u to the 4th over 4, which is my antiderivative, from 1 to 2. Now notice that I don't need to substitute x back in when I do this. So 1/2, 2 times 4 is 8, so 1/8. Now I'm going to substitute back in. I'm going to ignore my constant. Okay, so 2 to the 4th is 16, 1 to the 4th is 1. So I get 15/8 as my area. Okay, let's try number 2. I'm going to let u equal sine of x. That's a better choice because then my du is just cosine of x dx, right? So that's my du, and that whole sign there is my u. So I get u du, and I'm going to change my limits of integration. I plug in 0, substitute 0 in for x, I get sine of 0 is 0. And I plug in pi over 6, I get sine of pi over 6 is 1/2. So now I take the antiderivative and get u squared over 2 from 0 to 1/2. So now I get 1/2 of u squared from 0 to 1/2. So I get 1/2, I plug in a 1/2, I get 1/4 minus 0. So I get 1/8. And notice the beauty of this is that I do not have to substitute back in for x. I've made a total transformation of the variables, including the limits of integration. Let's try another. Alright, so I'm going to let u equal 1 plus x to the 1/2. So du is 1/2 x to the minus 1/2 dx, or 1 over 2 square root of x dx. Well, I almost have that. So if I put a 2 down here, which is really a 1/2, I need a 2 on the outside. So I get 2 integral. Again, this here is my du, and this inside here is my u. So I get 1 over u squared du, and I'm going to change my limits of integration. So I get square root of 1 is 1, plus 1 is 2, and plug in 9. Square root of 9 is 3, plus 1 is 4. I'm going to rewrite this integral as u to the negative 2 du. So I get 2 u to the negative 1 over negative 1. It's my antiderivative from 2 to 4. So that's negative 2, 1 over u from 2 to 4. So it's negative 2, 1/4 minus 1/2. Well, a fourth minus a half is, let's see, I'm going to do some scratch work over here. 1/4 minus 2/4 is negative 1/4. Okay, So negative 1/4 times negative 2 is 1/2. So again, the beauty of this is as long as you change your limits of integration here from 1 to 9 to 2 to 4, you don't have to sub your x's back in. All right, one last example. All right, I'm going to let u equal 2/3 of x, or 2x over 3. So my du is going to be 2/3 dx. Well, I don't have a 2/3 dx, so if I substitute in a 2/3 there, multiplied by 3/2 on the outside, 3/2 times 2/3 is 1, multiplicative inverse, right? So, and multiplying by 1 does not change a value. So, again, new integral, which of the cosine of u du, I'm changing my limits of integration, so 2/3 of 0 is 0, and 2/3 of pi over 2. Well, that might be tricky without a calculator, so I'm going to do 2/3 times pi over 2, 2's cancel, that's definitely pi over 3. So we get 0 to pi over 3, cosine of u du, the integral of cosine is sine, so we get sine of u evaluated from 0 to pi over 3. Which is my new limits of integration. So I get sine of pi over 3 minus sine of 0. So sine of pi over 3 is root 3 over 2, and sine of 0 is 0, so the answer is root 3 over 2. And that's how you change your limits of integration to evaluate integrals to find area or also volume. And there's my little note cards, okay? Good luck.